Welcome to my channel. Today I will discuss about the relative humidity part 3. The main purpose of this section is to understand the flow rate in each stage of compressor in multi-stage air compressor. The flow in multi-stage compressors in stages are different. The maximum flow is in first stage and it starts decreasing in the higher stage. This is due to the fact that water vapor gets condensed in each stage. The second point is that to know how to calculate the water vapor condensate in each stage. This topic is very useful for sizing of multi-stage air compressor. Topics of discussion: mass of dry air. We'll see how to calculate mass of dry air. Then next is water vapor condensation. So what are the effects which cause the water vapor condensations? Flow rate in the air compressor. So we have to calculate the flow rate in each stage of compressor, and then how to calculate the water vapor condensation in each state of the compressor. Mass of dry air. Calculation of mass of dry air. Let's say md is the mass flow rate of dry air in kg per hour. mb is the mass flow rate of water vapor per kg of dry air in kg per hour. mvt is the total mass flow rate of water vapor in kg per hour. ms is the mass flow rate of moist air in kg per hour. So total mass flow rate of water vapor is equal to mass of water vapor per kg of dry air into mass flow rate of dry air. So we can write mvt is equal to mb into md. Mass flow rate of moist air is equal to mass flow rate of dry air plus total mass flow rate of water vapor. So we can write ms is equal to md plus mvt. Again ms is equal to md plus mb into md, because mdt is equal to md into mb into md. So we can write md is equal to ms upon 1 plus mb. So mass flow rate of dry air is equal to mass flow rate of moist air upon 1 plus mass flow rate of water vapor per kg of dry air. So this formula is used to calculate the mass flow rate of dry air in compressor in last stage. The next topic is water vapor condensations. Condensation of water vapor occurs when moist air reaches to the saturation condition, and it normally occurs at heat exchanger, air cooler outlet in compressor system. Maximum water vapor carrying capacity of moist air depends on pressure and temperature at which it operates. So there is a relationship: increase in pressure reduces the water vapor carrying capacity, or vice versa. Increase in temperature increases the water vapor carrying capacity, or vice versa. So in compressor, increase in pressure will reduce the water vapor carrying capacity, and increase in temperature will cause increase in water vapor carrying capacity. And that is why there is no condensation when there is a compression, but condensation occurs when it has cooled to air cooler. If the moist air is carrying certain amount of water vapor, and due to change in pressure and or temperature, maximum water vapor carrying capacity reduces, then condensation occurs and excess amount of water vapor gets drained in cooler. So amount of water vapor which gets condensate is drained off from each cooler. So we will see also how to calculate the condensate recovery in the stage of cooler. This is a schematic for 3-stage air compressor, where compressor 1 with cooler 1, compressor 2 with cooler 2 and compressor 3 and cooler 3. Compressor takes the suction from atmospheric condition. We can write PT1, TT1, RH1, and similarly for intermediate stage pressure P2, T2, RH2, similarly P2, PT3, TT3, RH3, and for final stage it is PT4, TT4, and RH4. So P1, T1 is atmospheric pressure and temperature, and RH is atmospheric relative humidity. P2 and P3 are intermediate stage pressure, T2, T3 are intermediate stage temperature, RH2 and 3 are intermediate stage relative humidity. P4, T4 are final outlet pressure and temperature, and RH4 is a final outlet relative humidity. As condensation occurs at intermediate stage, so RH2 and 3 will be 100%, and also as condensation occurs at final stage, so RH4 will be also 100%. This is very important point that needs to be taken care while calculating the mass flow rate in each stage as well as condensate recovery. What are the data given in normal condition, and what data needs to be considered, and how we can calculate the mass flow rate in stages and condensate recovery. Given data is final stage mass flow rate. Normally client provide the mass flow rate at final stage, atmospheric pressure, temperature and relative humidity, intermediate stage and final stage pressure and temperature. This pressure is assumed here for understanding for calculation of intermediate stage pressure, intermediate stage flow and condensate recovery. Data to be considered: as the condensation occurs at intermediate and final stage, so relative humidity is 100%. That has to be assumed. The steps to be followed: saturated water vapor pressure using equation PV is equal to 0.61121 e to the power 18.678 minus T upon 234.5 into T upon 257.14 plus T. So that equation is used to be, that has to be used for calculation of saturated water vapor pressure. Then next calculation is such a vapor pressure of water, which can be calculated as PV is equal to RH into PVS upon 100. PVS is known, RH is known, so we can calculate the PV. Mass flow rate of water vapor per kg of dry air is equal to MV is equal to this equation. With this equation we can calculate this. Mass of dry air MD is equal to mass of water vapor at final stage upon 1 upon mass of water vapor per kg of dry air at final stage after the cooler. This equation is used for calculation of mass of dry air. Mass of dry air is same for in all stages, as dry air doesn't condensate. Total mass of water vapor in stages is equal to mass of water vapor per kg of dry air in stage into mass of dry air in stage. Total mass flow rate in stage is equal to mass of dry air in stage plus total mass of water vapor in stage. Water vapor condensates, we can call it previous is equal to previous stage of total water vapor minus present stage of total water vapor pressure. No, sorry. It should be like this. Water vapor condensate is equal to previous stage of total mass of water vapor pressure minus present stage of total mass of water vapor pressure. Water vapor, it is a mass. Understanding with an example: in 3-stage air compressor, atmospheric conditions are pressure is 1.013 bar, temperature is 30 degrees Celsius, and relative humidity is 70%. Intermediate stage pressure are 2.5 bar absolute, 5.5 bar absolute, and 5.5 bar absolute, and corresponding temperature in intermediate stage is 35 degrees Celsius. The final outlet mass flow rate is 30,000 kg per hour. Calculate the intermediate stage flow rate and condensate in each stage. How we can calculate this? What are the given data? Final outlet pressure flow rate is given, which is we can call MS is 30,000 kg per hour. P1, P2, P3, P4 are 1.013, 2.5, 5.5 and 8.5 bar absolute. T1, T2, T3 and T4 is 30, 35, 35, 35 degrees Celsius and atmospheric relative humidity is 70%. Data to be considered as the water vapor gets condensed in intermediate stage of air compressor. Relative humidity in each stage is 100%. That has to be considered. Now we'll see the calculation. Total mass flow rate at final stage after the cooler we can call 30,000, it is given. So input data we have written in this color is given. Atmospheric or inlet of stage pressure P we can write in KPI now, kilopascal absolute, 101.3, 250, 550, 850. Atmospheric or inlet of stage temperature T we can write 30 degrees Celsius, 35, 35, 35. Atmospheric relative humidity or intermediate relative humidity RH we can write 70. So these data is given. 100, 100, 100 is considered. Using the Buck equation, saturated water vapor pressure you can use based on temperature. So we have calculated kilopascal absolute is 4.244, 5.625, 5.625, 5.625. Vapor pressure of water, you can write PV is equal to RH into PV is equal to 100, which is 2.97 is first, then 5.625, 5.625, 5.625. Mass of water vapor per kg of dry air, we can write this equation 18.015 upon 28.96 into PV upon P minus PV, which is coming out 0.0188, 0.0143, 0.0064, 0.0041. Mass of dry air, MD is mass of total mass of water vapor, total mass flow rate at final stage upon 1 plus mass of water vapor at final stage after the cooler. So this color, so this equation is used here. So you have to divide 30 upon 1 upon this 0.004. You will get 29,876. As I said, this is a dry air, so this dry air will be remain same for all stages. So same data has been entered here. Total mass of water vapor, just multiply MB into MD. We can write, we know the MD and we know the MB. So just multiply these two, it becomes this. So multiply these two, it becomes this. Multiply these two, become this. Multiply this to this, become this. Now, total mass of flow in each state, we can write MD plus MBT. We can add. This is dry air plus total water vapor. You can add these two, becomes this. This is 30,438 is a total mass flow rate in first case. Then second higher stage, you can add this plus this, which is 30,304. Then this plus this become 30,068, and this is 30,000. So you can see in each stage there is a flow, and maximum flow is in first stage, that is 30,428, and minimum is the final stage. Now to calculate the water vapor condensation, we can calculate previous stage of total water vapor, mass of total water vapor, minus present stage of mass of total water vapor, that is mass of total water vapor is this. So you have to calculate here, so this minus this, 561 minus 428 becomes 133. Similarly for this case, 428 minus 192 becomes this, and for this case 192 minus 124 becomes 68. So with this we have calculated total flow rate in each stage and condensate recovery. So with this I have finished my lecture. Hope you will like this. Please subscribe it, like it and share it. See you in the next discussion. Till then, bye bye. Thank you.